Good afternoon, everyone. Today I'll be talking about the atmospheric escape from M-Dwarf exoplanets and the implication for long-term climate evolution and habitability. I would like to thank my co-authors who made great contributions to this line of work. And first, I will talk about motivation, followed by model description and input. Then I will give you 3 examples as Ocean Planet, Proxima b, and the TRAPPIST-1 System. Finally, I will give you the summary. So first, I would like to show you the habitable zone of our solar system. It is important to point out Mars is actually in the habitable zone of our solar system, which is usually defined by the location where liquid water can exist on the planetary surface. However, as we know, today's Mars has almost no atmosphere, only 6 M-bar left. And the surface and the climate is very cold and dry. So how Mars lost its atmosphere? I know some of you already see this animation before, but I found it's really fun to show it again.
Mars, the red planet, cold, dry, inhospitable to life. But billions and billions of years ago, Mars looked like this. There were lakes, rivers, oceans, the perfect conditions for life to form. So, what happened? Why was life unable to take hold? Where did the water go? We may never know.
There's some delay anyway. So you can see later there's a movie, and so the animation asks a good question: where did the water and atmosphere on Mars go, transforming Mars from early warm, wetter water to the cold and dry state existing today? And the animation gave you one possible answer about basically the impact. And today my talk will mainly focus on the solar wind erosion. So basically, the charged particle from the sun can make a great contribution to strip away the Martian atmosphere. It's very slow. Yeah, as you can see, the Mars atmosphere lost. And Bruce Jakowski will give you more detail in next talk. And this idea is actually supported by the MAVEN. As you can see, the charged particle is from simulation and the background from MAVEN observation, and they are reasonably agree with each other. And first, I will introduce you. The first model I use today is called 3D Butterus multi-fluid MHD model. We developed recently for the water worlds. We include the solar wind proton and water ion and electron. In order to capture the scale height variation in the thermosphere, we use highly adaptive mesh refinement. So the smallest resolution at the inner boundary is about 5 kilometers, and the inner boundary starts at 100 kilometers. And we include the photoionization, charge exchange, electron impact ionization, and electron recombination. In the coordinate system, the x-axis is from the star, from the planet to the star. So the solar wind or the stellar wind velocity is in the negative x direction. And the second model we used is called the Alfvén wave solar model. Because in our solar system we can measure the solar wind by the spacecraft, but in those exoplanetary system, there's no way to accurately measure the stellar wind at maybe at the next 20 years. So we use this model. Basically, we use the observed-based magnetogram, or there's a technique called ZDI map as the inner boundary condition for the stellar wind model, and which can drive the stellar wind as the inflow boundary condition for the planetary component. So the first example is I apply this model to the ocean planet, and basically I put ocean planet at 1 AU, and I use the current solar wind condition and the early solar wind condition about 3.9 billion years ago, and a supercurrent space weather event. The takeaway here is the ion escape rate is enhanced by more than 2 orders of magnitude during a space weather event. And the up panel here shows you how the water ion escape from the planet, and the bottom panel shows you the plasma boundary. As compared with the first column, the third column, we can see the plasma boundary is significantly compressed. And due to the reconnection on the day side, there's more open field line on the polar region, and those open field line can provide ion escape channel, as mentioned by the Kevin's talk. And where those ions come from, they can be photoionized, electron impact ionized, or generated by charge exchange. So this slide shows you exactly how those ions escape from the polar cap. And during the current time event, those ions has high velocity and more open field lines, so the ion escape rate was also enhanced. Fortunately, Earth-like ocean will not be evaporated over billion time scale, as the ion escape rates are way too slow for a sun-like star. However, the story may change for M-Dwarf, as the previous talk mentioned. The M-Dwarf are much more magnetically active. And if there's no surface liquid water on the planet's surface, then it will more look like this for all the M-Dwarf exoplanet. So the first example I applied to Proxima b, and as shown on this slide, compared with our own Mercury, the Proxima b's orbit is much more closer to the star, and due to the smaller and dimmer of the star. However, those stars, as I mentioned earlier, is much more magnetic active. And so we used the Austin model to simulate the stellar wind, because the stellar wind vary over one Proxima b's orbit. So we choose 2 points. One is the C1 corresponding to the maximal dynamic and the total pressure, and the C2 corresponding to the minimal dynamic and total pressure, but the maximal magnetic pressure. As we can see, compared with Earth, the solar wind, the stellar wind, the density is much higher, and the velocity is also much faster, and the magnetic field is also much stronger. So here I show you the how those. By the way, here I use a Venus-like atmosphere for the Proxima b, and here I show you how those O+ ions escape from the planet. And no matter it's unmagnetized or it's magnetized, as long as the stellar wind pressure is maximal, there's no close field line on the day side. So we can expect the ion escape rate will be very similar. However, for magnetized case, with C2, basically is the minimal total pressure. There's still some close field line on the day side. So those, so the magnetic field can still protect the planet to a certain point. And as we expected, only the C2 minimal total pressure with magnetized case, the ion escape rate is about 1 order of magnitude lower than all the other cases. And based on the atmospheric depletion timescale, we argue only this case has the potential for habitability. We also test different surface pressure. For example, we use the 93 bar as the Venus surface pressure. We found the atmospheric escape rate has no significant dependence on the surface pressure. But fortunately, the ionospheric profile are mostly unaffected by the stellar wind condition below 200 kilometers, no matter it's magnetized or unmagnetized, or both C1 and C2 cases. So I would argue if it's unmagnetized, it's will be more look like Mars. If it's magnetized, it will it's potentially maybe look like Earth. But there's no single conclusion about magnetized case is very complicated. And I am writing another paper, so there's no simple answer for the magnetized case. And for chapter 1, there's 3 planets in the chapter 1 system is in the habitable zone. And however, even the outermost planet is still much closer to the star compared with our Mercury. And I calculate the ion escape rate from the TRAPPIST-1 system, and as we can see, the atmospheric escape rate decreased monotonically with the star-planet distance. And based on the ion escape rate, we find only TRAPPIST-1G and H has the potential to be habitable. However, TRAPPIST-1H is not in the habitable zone in the TRAPPIST-1 system, so we argue TRAPPIST-1G will represent the best chance for a planet in the habitable zone of this system to support a stable atmosphere over long periods. Here I show this is an ongoing work, and here I show you a potential stellar CME from a young sun-like star. Because of the fast rotation of the star, so the CME affected region become much more broader in the longitudinal direction. Every coin has two sides. Although I mentioned a lot of negative side of the stellar activity, but it also has a positive role in on the probiotic chemistry, because N2 can easily be broken to N and N plus by those energetic particles from the stellar event. And if we have O or ozone, or O2 or ozone, and with some methane, which can form the hydrogen cyanide, which is critical for the probiotic synthesis. So the conclusion here is the exoplanetary space weather and stellar wind-induced atmospheric escape is very important for planetary habitability. Thank you very much.
Do we have some questions? We have one right here.
So interesting talk. Good talk. I just had a comment. So yeah, I like your results here. I would argue that still that TRAPPIST-1H would probably still be your best bet. I mean, when you're looking at the habitable zone you're using, the three planets in the habitable zone, you're using the classical CO2 water habitable zone.
Yes.
But on a small planet like H, it's possible that you could have had hydrogen. We wrote a paper 2017 on volcanic hydrogen. You can extend the CO2 water definition with hydrogen, and actually TRAPPIST-1H just barely makes that definition. So I mean, there's
Yeah, I agree. I know your early paper also about the early Mars. About the hydrogen warming.
Yeah, so we extended that concept here, and H is a small planet, so it could have a reducing mantle, and there are things that could favor having a denser hydrogen atmosphere for that. So yeah, I also like H just because also the period at which it have a smaller period that it be in these high energy flux situation, high runaway greenhouse conditions early on. It's farther away from the star, and that'll help with the escape compared to the planets closer in. But
I see. Thank you.
Hi, great talk. How does the ion escape change as a function of where you are on the maybe the outside or the inside of the Alfvén radius, for especially Proxima b?
You say inside or outside Alfvén surface or what?
Yes.
For Proxima b, I found, at least from my simulation, all of them are outside Alfvén surface. But for Proxima b, but for TRAPPIST-1 system here, the TRAPPIST-1b is inside the Alfvén surface. So as you can see, so you're asking the analytical estimation, right? Or you are asking
just the ion fluence at the distance of the planet. Does it increase or decrease, or you see no difference between the two cases?
Basically here is the ion escape rate change with the star planet distance. And so I'm not sure whether I understand your question correctly. You are asking about inside the Alfvén surface and outside Alfvén surface. What's the ion escape difference? Then, because one interaction is subsonic, one interaction is supersonic, and based on my previous Mars simulation, I found the subsonic interaction will actually enhance the ion loss. But for this system, I'm not sure. I need to check.
All right. Well, thank you very much.